Hi, Chem students. Let's continue our discussion of entropy, this new variable that we have out there. We've kind of found a reason to have it, and let's put it to use. So here we go. There's a lot of ways to think about what entropy is, and because of that, there's lots of ways to actually talk about the second law of thermodynamics. But for us, it's more important that we just understand it in one context, and that is entropy is going to be defined as this measure of some dispersal of the energy in the system. So by dispersal, I want you to think about that plate breaking once again. When it hit the ground, it spread out that energy. And so in other words, energy doesn't like to be concentrated in one spot. It likes to be spread out. We see this as the universe expands. The energy of the universe is pretty much constant, and therefore as the universe expands, we're seeing the energy spread out. One of the easiest ways to look about this is that System 1 and System 2, if these two systems somehow interact and we let some energy transfer, let's say in the form of heat, that's how it's going to get transferred, then we can say that there's going to be an entropy change if System 1 and System 2, if they store the energy differently. Now you might be thinking, well, what do you mean store it differently? Well, objects can have many ways to store energy, and it has to do with, when we get down to it, the very nature of chemicals themselves and chemical bonds. And so I guess, the best way to do this is to show you an example of exactly what I mean. And that's right here. So if we take a look at these two molecules here, the one on the left, that is called ethane, and the one on the right is called methane. So we've got two molecules, and if you take a look at these guys, you'll notice there's a difference in the variety of bonds, the types of bonds there are. In ethane, there's carbon and hydrogen bonds, but there's also a carbon and carbon bond. So there's two different types of bonds, and in addition to that, there's more bonds in the ethane. So this molecule on the left has a lot more ways in which the energy can be put into it. There's more variety. Therefore, there's more ways to spread the energy out. So we would say that the ethane, the molecule on the left, has a higher entropy than the molecule on the right. All right? Why? Because it has more ways to disperse that energy. It can put that energy into more ways of bonding, and it can also put it into these other aspects. There's vibrations and rotations that can occur in ethane that can't occur in methane. So there's a lot of differences here in terms of the number of bonds, the types of bonds, the number of vibrations, the way it can vibrate. All of those things play a part in how that energy is stored. And rotations and vibrations, those things are just types of kinetic energy. All right, so that's what I mean by energy is dispersed. If I give ethane and I give methane the same amount of energy, that energy is going to be distributed differently between the two molecules. And it's very similar to if I came to class tomorrow and I gave everyone in the class $100. Not all of you would spend it the same way. You would disperse that into your own world and in what is necessary for you. Some of you may have to pay off bills. Some of you may go, hey, I can go finally buy that new book I want, or that new computer is closer to being in my possession. Whatever it is, everyone's going to be different on how they disperse that energy. These molecules, if we give them both 100 joules, they're going to spread that out amongst themselves differently. What else can we do? Well, early on in the annals of entropy became this definition that it was a statistical type phenomena. So what happened was Boltzmann was able to come up with an expression for entropy in terms of the ways in which the system, whatever it is, whether it be a chemical or it be some kind of physical system, the way it could be arranged. And he called these things complexions. And so just think about this as the number of arrangements that you can put something in. And it turns out that the more arrangements you have means there's more ways to disperse the energy. And therefore, there'd be a larger entropy for that system. So just as a simple example, let's look at something as silly as two balls being put inside a box. Now the box is going to have dividers in there. So let's imagine this box right here. Okay, this box has a volume of looks like four little squares that are roughly the same size. And if we have two balls, there's two ways to put those balls in, I'm sorry, there's six ways to put those two balls inside these four dividers. And I've shown all six of those, so we would say there's six complexions because there's six ways to arrange this. However, what happens if I make this box just a little bit bigger? I give it two more. I've increased the volume, or give it two more positions. Well, as soon as I do that, believe it or not, I can have now up to 15 positions. So there's 15 ways to arrange the energy in a box that's a 3 by 2. And because there's more complexions, that symbol that we saw above, that omega, is now larger. And since it's larger, we can immediately say that the entropy of this lower system, the system with 6 container spots versus 4, we can say that it's got a higher entropy. Now, what happened here physically to the system is we actually just added more space. We made it a larger volume. And we've come up with a neat little rule. And that is, if we hold everything else constant and we only change the volume, we make it bigger. If we increase the volume, we see an immediate impact, an immediate increase in the entropy. So there's not a lot of always in the world of science, but this is one of those true this is one of those few always. And that is, if all else is the same and I increase the volume, I will increase the entropy. Why? Because I'm creating more space for the energy that's there to exist in. And that spreads it out. So there it is. All else being equal, if I increase the volume, the entropy will increase because there's more space to distribute the energy. Wow. Let's try something else. Let's look at one more example. And it's my favorite graph. Yay! The Maxwell-Boltzmann distribution. You guys should be just completely ready for this by this time. And we're looking at the same gas at two different temperatures, all right? And so what I'm going to say is, we've got this gas. It's in a container. It's the same volume. All we're going to do is increase the temperature. And when we do that, let's look at the realistic velocities. I mean, granted, this thing goes on forever, ever in this direction, right? It goes on until we get, not really to ever, it goes to the speed of light. The key thing is that the velocity that we have there, that velocity, there's really only a realistic end to this. So if I look at the cold one, it ends about right. Let's see if I can get this to work. It ends about right here. And I've kind of drawn a line down here. So you can see here's the range of realistic velocities for the cold gas. How about the warmer gas? Well, the warmer gas, I start to see that the probability becomes close to 0 way over here. And this has a little bit larger range of velocities. So I want you to think about this. The higher temperature gas has more possible ways to move. It can move at higher velocities. More of them are realistic. So we've just learned something really cool. If there's more ways to move, that's more ways to arrange the system. That means there's more complexions and the entropy is larger. So if all else is equal and we increase the temperature, we're also going to see an increase in our entropy. Fantastic. So we've got this entropy thing and we know some rules about it. And we can now calculate anything we want with it if we had numbers for it. So let's just imagine that there is a way to measure those numbers, okay? And there is, but we're not going to go into that. The key thing is we now have this variable. It's a state function, okay? And it's called entropy. It has units that are very odd, joules per Kelvin mole. And if we had a lot of time, I would go into why we should change the units for entropy to no units at all. It would make me happy, but no one else. So the key thing here is that it has some units that are always joules per Kelvin mole for us, and it's a state function. Like enthalpy then, because it's a state function, we can compile a table of enthalpies of formation. Okay, it's slightly different. It's slightly different. When we look at enthalpy, we find tables of changes of enthalpy of formation. Well, these are just true entropies of formation. And that has to do with the third law of thermodynamics, which says that there's a definite place that we can call a 0 for all substances. So it's not very important. The key thing is when you see the tables, the H that we have, the enthalpy, will have a delta in front of it and that little F and the little naught, while the entropies will not. And just like we did before, we use the same type of Hess's law calculation to compute a change in entropy for a reaction. That's right, the reaction can have a change in entropy, and it's due to the differences in entropies between our products that we started with and the reactants that we ended with. In other words, each of these molecules is holding on to the energy in a different way, and when I rearrange the bonds, I'm going to rearrange the way that energy is distributed amongst all the molecules. So even though I've conserved mass, and even though you conserve energy, when a process occurs, the rearranging of the bonds is going to rearrange how the energy is stored and how it's distributed, and that means the entropy will change. So very simply, if you take a look here, we've gone through the same reaction, and this should look very similar to what you saw before. It's the sum of the products minus the sum of the reactants. Just to remind you that we're still going to keep using these stoichiometric coefficients in our reaction to tell us how many of those particular guys we have. So here's just one last example. How would we find the standard entropy for P4 solid plus 5O2 goes to P4O10? And we would probably go look those up in the back of a book. You should try these two examples here before you come to class. See if you can calculate these by looking up these values in a table. By the way, I'm going to post one of those on the blog very soon. So we're about ready for class. Watch these videos, take a few notes, read it in the book, and try to get a handle for this. Entropy is challenging. So if you're a little bit confused about it, don't worry, that's normal. It takes a long time to get a handle on what entropy means. So I recommend, though, that you watch this video again.